As I said, our last section, proof by cases. Well, it says here we can go on and on, and on, and on, and on. It sounds like an ABBA song. About different proof styles. We haven't even mentioned induction or the combinatorial proofs here. We did them earlier. But instead we will end with one final useful technique, the proof by cases. The idea is to prove that P is true by proving that if P, then Q, and if not Q, then P, for some statement Q. So no matter what, whether or not Q is true, we know that P is true. In fact, we could recognize this. Okay, and he goes on to say to prove it for every single case. Okay, so just to summarize, to prove that P is true, we prove that if Q, then P, and also if not Q, then P, for some statement Q. Okay, let's see how this works by example. Okay, our example is going to ask us to prove the following. Prove that for any integer n, the number n cubed minus n is always even. We want to prove that. Okay, so remember, it's a universal statement for any integer n. We want to prove that n cubed minus n is always an odd number. Well, folks, it is hard to know where to start with this, because we don't know anything about n other than the fact that it's an integer. We might be able to prove that n cubed minus n is even if we knew that n was even. Okay? In fact, we could probably prove that n cubed minus n is still even if n is odd. But since n must either be even and odd, we don't know. We will work with both. Okay, so let's see how we do our proof. Our proof is as follows. We consider the two cases. The first case, if n is even. Okay, so we're going to work first of all with n that is even. Now, we've done this so many times. What does it mean if n is even? It means that n can be written as twice something where k is an integer. So n can be written as a multiple of 2 in plain English. Now, what does that mean for this statement? Well, let's have a look. So therefore, n cubed minus n will be 2k cubed minus 2k. Now all we need to do here is remove that is going to be what? 8k cubed minus 2k. If I remove a 2, that's all I need to do, then I have 4k cubed minus k. Now what is that? That is even. This is even. Why? Since k cubed minus k, or 4k cubed minus k, is an integer for k that was an integer. So if k is an integer, 4k cubed minus k is also integer, which makes this a multiple of 2, which makes it even. So therefore, n cubed minus n is even, if n is even. Let's go and look at the second part. What happens if n is odd? If n is odd, well then we learned we can write n as 2k plus 1 for some integer k. It's even plus 1, which means it's odd. Okay? Now what does this mean? What does this mean for that statement up there? What does n cubed minus n become in? Well, let's see. Let's substitute in. We get 2k plus 1 cubed minus 2k plus 1. Now, all I need to do here is remove 2k plus 1, and let's see if I distribute the square over there. I get 4k squared plus 4k plus 1 minus 1. and that leaves me with twice k plus 1. I'm really just manipulating here now. That is 4k squared plus 4k. From there I remove a 2. Hence it doesn't matter anymore. I've just written this as a multiple of 2. So 2k plus 1 and 2k squared plus 2k is what stayed behind. Now that means that this is even. Let's see why it's even. Well, is even. Why? Because 2k plus 1 is an integer. Because k was an integer. Okay? And the second argument is that 2k squared plus 2k is an integer. Because k again was integer there. So therefore, n cubed minus n is even when n is odd. Okay, so is the statement true? Indeed. We've just shown that it's indeed always the case that n cubed minus n will always be even for any integer value of n, whether it's even or odd.